Alright, thank you for watching. And because you liked that video about the sum of cosines, I'm happy to tell you there's also another amazing simplification if you consider the product of sines. For example, if you take the product of this formula, let's say with n equals to 6, I will show you something like n equals to sine over pi over 6, sine over pi, 2 pi over 6, sine of 5 pi over 6. I will show you that this actually equals to 6 to the 2 to the 5. Okay? And you may say, how can I get this? Well, let me show you. It involves a little bit of complex numbers, but actually not much. And by the way, this is not my original proof. It's given by another doctor of math called Dr. Anthony on the math forum. Okay, but still, really, really nice proof. Namely, let's start with some very strange equation. So consider the following equation of degree 2n, x to the 2n minus 2x to the n cosine of na plus 1 equals to 0. So, I really love this argument because it's a very argument a la flammable maths. So you'll see, we'll consider this equation which depends on a positive n, a positive number a, and then we will choose what our a is. In fact, we won't really choose it. We'll let a go to 0. So consider this equation, and notice it's an equation of degree 2n, so there should be 2n solutions. And in fact, surprisingly, we are able to solve this equation explicitly, because notice, this is the same as x to the n squared minus 2 cosine of na x to the n plus 1 equals to 0. So, if you let y to be x to the n, this really becomes y squared minus 2 cosine of na y plus 1 equals to 0. So this is a second degree equation. Let's solve it with the quadratic formula. So y equals to 2 cosine of na plus or minus square root of this squared, so 4 cosine squared na minus 4ac, so minus 4 over 2a, 2 times this coefficient, which is 1. And then you're left with cosine of na plus or minus, the 4 here comes out, so we have square root of 4 times cosine squared na minus 1, but cosine squared na, it's minus 1 minus cosine squared na, and that's minus sine squared na. And again, this is also still over 2. And so we get cosine of na plus or minus 2 over 2. And the square root of minus sine squared na becomes I sine na. And n is positive, and we let a go to 0, so a is close to 0. So this sign is positive, and therefore the answer is I sine of na. Because you have minus sine squared of na, the 2's cancel out, and then we're left with y equals to this very nice formula. So y is cosine na plus plus minus I sine na, which, if you like, you can just write this. You see, this is equal to either cosine of na plus I sine of NA, which is equal to the EI NA by de Moivre's formula. Black pen, red pen, I'm watching you, okay? Or it equals to cosine of NA minus I sine of NA, which is the same as cosine of minus NA plus I sine of minus NA, which is e to the minus INA. So in other words, y equals to e plus or minus INA. But what was y? It was x to the n. So what we really get is x to the n equals to plus or minus e to the INA. But now, remember that y is x to the n, so equals to e to the NAI. And now, remember that we want n solutions. So in order to have n solutions, we'll just add multiples of 2 pi. So 2 pi k. And also, the same thing for e to the minus NAI. And technically what we want to do is adding multiples of 2 pi k, but in order to have a certain symmetry, and you'll see in a second why this is useful, you just want to subtract multiples of 2 pi k, where k goes from 0 to n minus 1. And you'll see in a second why this is useful. And now we can take n roots. So x to the n is e to the ai, sorry, I forgot i's here. If you e to the a, I guess na plus 2 pi k over ni, and e to the minus na minus 2 pi k over ni. And therefore we get that x equals to e to the a plus 2 pi k over ni, and e to the minus a minus 2 pi k over n. Guess this thing, minus a minus 2 pi k over ni. And notice you can conveniently write the latter term as e to the minus a plus 2 pi k over ni. And this is for k goes from 0 to dot 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 to n minus 1. Alright, what does that tell us? It tells us that those are the roots to our equation, and because those are the roots to our equation, it means our equation can be written as x minus each of those roots. So therefore, we have the following. x0, which is again x to the 2n minus 2x to the n cosine of na plus 1, can be written as the product over k's from 0 to n minus 1 of x minus this factor e to the a plus 2 pi k over ni times x minus e to the minus a plus 2 pi k over ni. In other words, you take x minus this, those give us 2 roots. But since this is true for all k, we can take the product over all k. And by the way, here we get 2 roots, but over n numbers. So we indeed get 2n roots, and this is equal to 0. I believe those are all distinct because a is positive. So I think that's the main reason why we chose a positive. Okay, and now the next step is, let's consider the term, in the product. And it turns out we can simplify this a little bit to get back to the real world, so step 2, note that if you take x minus e to the a plus 2 pi k over an I, and then x minus e to the minus a plus 2 pi k over an I, you can FOIL it out and you get x squared minus, so the sum of those, if you like, x minus c times x minus d is x squared minus cx minus dx plus cd, cd. Okay. And we have x squared minus c plus dx plus cd. So here, if you use this formula here, we have to add those two roots. So e to the a plus 2 pi k over n plus e to the minus a, because I keep forgetting about the i's. So 2 plus k over n I. Okay. All right, and in fact, notice this and then x. Notice this does simplify, and I'll get to the constant term in a second, because e to the theta I plus e to the minus theta I, that's equals to 2 times e to the theta I plus e to the minus theta I over 2. But this is none other than cosine of theta by de Moivre's formula. All right, and lastly, so this becomes x squared minus 2 cosine of this junk here, a plus 2 pi k over n x. And lastly, the constant term becomes much, much easier. E to the a plus 2 pi k over n I times e to the minus a plus 2 pi k over n I. But then those things precisely cancel out, and this equals to 1. And by the way, this is precisely why before I chose this minus k, in order to make this formula work out, and also to have, the simplification here. So now we're back in the real world, so that's really cool. And in fact, this huge product is none other than the product of this junk over every k. So this is step 3. So step 3. Hence, x to the 2n minus 2xn cosine of NA plus 1, that's our original equation, now becomes the product from k equals to 0 to n minus 1 of those factors here. X squared minus 2 cosine of A plus 2 pi k over n x plus 1. And again, and that's because we found that this equals to this factor here, and we get that. Otherwise, we don't even have to worry about if it's equal to 0. What we really did here, we took this polynomial of degree 2n and wrote it as a product of second order polynomials. So, really, really cool. Right? And now that we have this polynomial with x, let's choose a certain value for x. So this is valid for every x. And now from now on, let x equals to 1. So let x equals to 1. And not only that, here we have a factor of 2. It would be nice if a also had a factor of 2. But no worries, let's just assume that a equals to 2 times the number b, and assume a equals to 2b, and again, b is to be determined. And then if you plug this in, in other words, if you now plug in both sides of the equality here, we get that on the one hand, we get 1 minus 2 cosine of n to b, so 2nb, I guess, yeah, 2nb or not 2nb, that is the question, plus 1 equals to the product from k from 0 to n minus 1 of 1 minus 2 cosine, again, of 2b plus 2 pi k over n plus 1. And you already noticed there's a big simplification here because 1 plus 1 is 2. Okay, so in this whole jumble we do have a nice identity. So 2 minus 2 cosine of 2nb equals to the product from k equals to 0 to n minus 1 of, again, 1 plus 1 is 2, so 2 plus 2 cosine of, the nice thing is, again, the 2's now, they factor out, 2 times b plus pi k over n. Now, let's just try to simplify the inequalities. So, and this is why we have this 2 here now, because we can use some identities. So, let's maybe focus on the first thing here. I guess let's call this A equals to B. So A is 2 minus 2 cosine of 2nb. But well, that's 2 times 1 minus cosine of 2nb. And now remember the nice identity, cosine of 2x is cosine squared of x minus sine squared of x. So this becomes 1 minus cosine squared of nb plus sine squared of nb. And you'll see in a second, it would be nice if we had terms of the same form. So for example, let's write cosine squared in terms of sine squared. So 1 times 1 minus sine squared nb, or no, not even that, easier than that. 1 minus cosine squared, that's sine squared, nb plus sine squared nb. And then that's 2 times 2 sine squared of nb, so we get 4 sine squared of nb. So nicely enough, the left-hand side becomes 4 sine squared of nb. And now let's look more importantly at the right-hand side. Let's look at that. So let's see. So b, so 2 plus 2 cosine of 2 times b plus pi k over n. Well, that's 2 plus 2 times. Again, now let's use the identity again. So cosine squared of b plus pi k over n minus sine squared of b plus pi k over n. Let's see how we can simplify that. So that equals to, I guess, 2 times 1 plus cosine squared of b plus pi k over n, okay, minus sine squared of b plus pi k over n. I apologize, there's a small typo here. I think at some point this was supposed to be a minus because we had x squared, x to the 2n minus 2x to the n. So this really becomes minus and minus. So sorry. minus this, minus that, so it becomes 1 minus cosine squared plus sine squared. And now it simplifies, because I was like, there should be a sine squared somewhere, but there is. So, we get 2 times sine squared of b plus pi k over n plus sine squared of b plus pi k over n. And then now it simplifies. This is 2 times sine squared. So in the end, we get 4 times sine squared of b plus pi k over n. And you'll see it's very nice, because now our formula simplifies. So therefore, b is really the product of those two things. K from 0 to n minus 1 of 4 sine squared of b plus pi k over n. However, notice each of those has a factor of 4, and we're multiplying this n times. So each contribution we have 4, so it's 4 times 4 times 4 times 4 times 4 n times, and you're left with 2 to the 2n. Okay. So what we have, so a equals to b. That means 4 sine squared of nb equals to the product k from 0 to n minus 1, 4 sine squared of b plus pi k over n. So what we get is 4 sine squared of nb equals to, I guess, 4 to the n, product from k equals to 0 to n minus 1 of sine squared of b plus k pi k over n. Okay, and now let's take square roots. Remember, there are no absolute values because, again, b is close to 0, so everything, I think it's between 0 and pi. So what we're left with is 2 sine of nb equals to 2 to the n. So it's 2 to the 2n, but square root is 2 to the n. Product from k from 0 to n minus 1 of sine of b plus pi k over n. And of course, you can simplify this a little bit, just a little bit. So sine of nb becomes 2 to the n minus 1, product from 0 to n minus 1, sine of b plus pi k over n. Which really becomes, let's just write this out, this product out. It's 2 to the n minus 1, sine of b, and then sine of b plus pi over n, sine of b plus 2 pi over n, dot, 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 sine of b plus n minus 1 over n pi. Maybe sine of n minus 1 pi over n. And notice, this looks very similar to our product, right? Because if b equals to 0, this part is in fact what we want. Sine of pi over n, sine of 2 pi over n, up to sine of n minus 1 pi over n. And in fact, to let this happen, the only factor that's kind of superfluous is the sine of b. So let's divide this by sine of b. Sine of b. So we have this thing here. And well, as I said, if you want to let b goes to 0, this goes to what we want exactly. And well, let's see what happens here. So I guess that's our last step. Step 4. Now, take the limit as b goes to, I guess, 0 plus of this side. Well, let's see. Limit b goes to 0 plus of sine of nb over sine of b. Oh, I think someone may have broken his leg because it's time for the L'Hopital. Okay, so to calculate this, use L'Hopital's rule. Limit b goes to 0 plus of cosine of nb times n, times n over cosine of b, and that equals to 1 times n over 1, and that's n. And then the limit as b goes to 0 plus of this thing, 2 to the n minus 1, sine of b plus pi over n, dot, 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 sine of b plus n minus 1 over n pi, this thing. Well, if we let this equals to, in fact, 2 to the n minus 1, sine of pi over n, sine of 2 pi over n, dot, 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 sine of n minus 1 pi over n. N minus 1 pi over n. Woo! Which is just what we want. So, if you want to equate this, you get that n equals to 2 to the n minus 1. Our answer, and therefore our answer equals to n over 2 to the n minus 1. Woo! How cool is that? So in fact, if we want for n equals to 6, we get 6 over 2 to the 5th. But wait, there's more! Because you may ask, okay, how cute, you found this formula, what is this useful for? And let me not quite reveal it yet, let me show you. Let's start with this equality and then see what happens. So, what do we have? We have, okay, maybe that's a bonus, in case you're still watching. So, sine of pi over n, dot, 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 sine of n minus 1 pi over n, that equals to n over 2 to the n minus 1. Well, here we have a product. Let's turn it into a sum. And how do you break a product into a sum? With ln degenerate. So ln of sine of pi over n, dot, 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 sine of n minus 1 pi over n, that equals to ln of n minus 2 to the n minus 1. And therefore, ln of sine of pi over n plus dot, 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 plus ln of sine of n minus 1 pi over n, that equals to ln of n minus ln of 2 to the n minus 1. So if you want n minus 1, ln of 2. And for reasons that become apparent in a second, let's take this and divide both sides by pi over n. So I guess, let me see. Yeah, or let's multiply both sides by pi over n, sorry. So pi over n times ln of sine of pi over n plus dot, 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 plus ln of sine of n minus 1 pi over n, that equals to pi over n ln of n minus pi over n minus 1, ln of 2. And now lastly, again for a second, apparent in a second, let's now take a limit. So limit n goes to infinity of this thing, ln of sine of pi over n plus ln of sine of n minus 1 pi over n. That equals to, well, ln of n over n, that goes to 0 by L'Hopital's rule. And this thing here, well, it goes to 1, if you want to factor out n on both sides. And in the end, you get minus pi ln of 2. And you might say, what is the big deal here? Well, notice, here we're summing up a bunch of values of ln of sine, and we're summing it up, and we take the limit. So in fact, this is basically the Riemann sum of ln of sine of pi over n. And this Riemann sum, well, it goes to the integral. So the integral of the first point, which is 0, and the last point, which is pi, ln of sine of x dx, we've just shown it to be minus pi ln of 2. Okay, there is the issue. I forgot one point, on the right-hand side, but I think you can maybe add it here. It doesn't affect the integral, or more easily, it's an improper integral anyway, so at pi, let's ignore this value. But anyway, so if you do this Riemann integral, and using this cool product, you in fact find that it's minus pi ln of 2. Which I've done in another video, but using a completely different means. But in case you're wondering why this is useful in life. Alright, thank you for surviving. If you like that and like more math, please make sure to subscribe to my channel. Thank you very much.